La la la. Doing princess things is my favorite thing. Stop, princess! I am Lord Hadron Collider. I will have to stop you. Oh no, please help me. Okay, princess, I will help you. My name is Prince Muon too, and I will kick this guy. Oh no, I got my math wrong. Sorry? What do you mean we're on air? Hello. Welcome to Skeptics in the Pub Online. My name is not important, but I'm happy to see so many of you online, I think. We, Skeptics in the Pub, used to meet in various pubs around the UK and further out, but this is the age of COVID, so we put our heads together and we started these online talks, which quickly grew into a lovely community with our own Discord server and various channels on social media. If you want more details, please watch out for the chat moderators providing more details throughout the talk. The same applies also for the links to our little shop. So if you want to sport something fashionable with our merchandise, follow those links. About tonight. As usual, we'll have a talk of about 45 minutes, followed by a short break for refreshments and comfort breaks, and then we'll close out the evening with a Q&A with our speaker. If you want to ask questions during the Q&A, please go to SitP-online/ask, and you will be able to put your questions there, and you will also see the questions that already have been put up, and you'll be able to upvote the ones that really interest you. You do not need an account to do so, but if you put down a name, it makes this whole thing more personal than just reading out anonymous asks. Good. Time to talk about tonight's speaker. We are welcoming Dr. Harry Cliff, who is a particle physicist at the University of Cambridge working on the LHCb experiment. He's member of an international team of several hundred physicists, engineers, and computer scientists, and he's using the LHCb to study basic building blocks of our universe. And he's in search of answers to some of the biggest questions we have nowadays in modern physics. But he also spends a big chunk of his time sharing his love of physics with the public. He just finished his first popular science book called How to Make an Apple Pie from Scratch, which will be published in August this year. Hopefully, I think we've got a link to pre-order if you're interested. Harry also has curated two major exhibitions at the Science Museum in London. And he has been giving lots of talks, including TED and at the Royal Institution, including television, radio, and various podcasts. I actually hope that after tonight, he might add our little event to his resume. Harry will be the first of several speakers that we have coming up in the next few weeks, who will all be working at the LHC or with the LHC, and we hope that you will enjoy this little Skeptics in the Collider talk series that we'll have coming up. Enough from me. Let's get started. I want to ask you all to put your hands together for Dr. Harry Cliff.
Oh, thanks very much for having me. I'm sorry we can't actually all be together in a pub. That would be a lot more fun than me sitting in my bedroom. But maybe I can grab a beer in the break before the Q&A. You might be wondering why a particle physicist is talking about apple pie. But some of you may know the reference, some of you may not. But in case you don't, the inspiration for this title was actually a title for the book I've just been working on. But it's sort of a way of thinking about some of the big questions that we're trying to answer in fundamental physics at the moment. But the inspiration comes from a 1980s TV series called Cosmos. So this was one of the first really big budget television science documentary series, and it was presented by Carl Sagan, who's sort of a sort of mythic figure in the pantheon of science communication, I guess. And you can see here, this is a clip from the start of episode 8 of Cosmos, and you've got Carl there wearing one of his signature turtleneck sweaters. And there's this slightly strange scene where the episode begins with this scene in a kitchen where an apple pie is being made with this like Blade Runner-esque soundtrack playing over the top. And then this apple pie is brought out to Carl Sagan, and he looks at the camera and says, "If you wish to make an apple pie from scratch, you must first invent the universe." And then he kind of goes on to talk about, where does the material in the apple pie come from? And the basic message, the reason sort of Sagan says this, it's a sort of pithy way of really saying that if you want to understand the origin of even a very mundane object like an apple pie, then you need to really understand the full history of the universe going right way back to the Big Bang. So this is sort of I guess the way we might phrase this in a sort of more scientific language, the question that Carl's really posing is, where does matter come from? So where does the stuff that makes up the world around us ultimately come from? And we've learned a hell of a lot about this question over the last couple of 100 years. And we've learned really, I mean, to grossly simplify, there have basically been two major sources of information about what the physical world around us is made from and where that stuff comes from. And those two places are, first of all, doing laboratory-based experiments here on Earth. So this began in the sort of 17th and 18th centuries with early chemistry experiments, and it goes all the way through to experiments like the Large Hadron Collider, where we're in a laboratory, albeit in this case a very big laboratory, studying the basic components of the universe at the sort of smallest possible scales, trying to understand how everything fits together and how those components interact with each other. So we have these lab-based experiments on Earth, and we've learned a huge amount through those sorts of investigations. And the other place that has taught us, the other way we've learned a lot about the matter in the world comes from astronomy, from looking at the universe at the largest scales. And this in terms of, particularly when we're trying to answer the question, where does matter come from? It's by looking to the stars and to the wider universe that we've managed to unravel a lot of this story. But to start the story off simply, let's begin with the apple pie. So this is actually an apple pie that I made last year. It doesn't look quite as nice as Carl Sagan's. I hadn't actually made an apple pie before. You can see it's a little bit burnt, but it's got all the basic things that an apple pie has in it. And I sort of started with a really quite silly experiment, which was to say, well, okay, let's imagine you were presented with an apple pie and you had no idea what went into an apple pie. You never heard of apples or flour or milk or eggs or whatever, and you wanted to understand its basic components, and you were a scientist. Well, what might you do? Well, what you might do is take a sample of the apple pie, and taking some inspiration from early chemistry, what I did was shove it into a test tube and then heat it up to a very high temperature with a Bunsen flame. And in the process of doing this experiment, basically what happens is the apple pie disintegrates and it breaks down into more basic substances. And what you broadly end up with at the end of this rather stupid experiment are a sort of charred remnant solid, which is mostly the sort of solid material of the apple pie, which is broadly speaking carbon. And then you end up with a sort of condensed liquid, which I put in a water bath at the other end, which is mostly water. So it's not a very sophisticated experiment. You can't really very easily figure out what the elements involved are here, but we kind of know that broadly speaking, an apple pie is mostly made from the elements hydrogen, carbon, oxygen, nitrogen, phosphorus, and a bunch of others as well, iron, a scattering of things throughout the periodic table. So, and this is sort of the way that, you know, our proper understanding of the material world really began, with experiments by people like Antoine Lavoisier back in the 18th century. And he was one of the first people to start to categorize what we now know as the chemical elements. And eventually this led to this very famous table, the periodic table, where all the elements were arranged in rows and columns with their patterns in their behaviors repeating as you move along rows and move down the columns. So if at the sort of, I guess at the late 19th century, if you ask someone what is the world made from, they would have told you, well, there are sort of 90-ish chemical elements or so, and each of those elements has associated with it an atom. So each element basically has a unique atom, which is a little hard, indestructible nugget of stuff, which is unique to every single atom. Now, this sort of atomic view of the world, if you were then to say, well, okay, where did the elements come from? Where did the atoms come from? Well, one response what you might get would be to be told that God had made it that way. So Isaac Newton, who was one of the sort of early advocates of the idea that the world is made of atoms, famously said something along these lines. He said, it seems probable to me that God in the beginning formed matter in solid, massy, hard, impenetrable, movable particles, by which he means atoms. So basically the idea is if these atoms are indestructible, they must have always been around. God made them at the beginning of time, and they've just hung around in the universe ever since. So if you take Newton's word for it, that's the end of the story, and it's sort of job done. We can all go home. But of course, we know that this is not the end of the story. So at the end of the 19th century and the start of the 20th century, there are a series of discoveries mostly made in laboratory experiments, in physics laboratories, and a lot of them actually in the UK. Most of these discoveries were made either at Cambridge University or Manchester in the UK, where the atom was gradually disassembled and smaller particles were sort of extracted from the atom. And we ended up with this model of the atom that we all learned about in school, where an atom is composed of this tiny nucleus, this red blob in the middle, and then is surrounded by this cloud of negatively charged particles called electrons. And so you now start to understand through this model where all the different chemical elements come from. It seems to be that their chemical properties are related to the number of electrons associated with a given atom. And if you go forward a bit further, so if you go sort of into the 1930s, experiments using radioactive elements and then later particle accelerators allowed physicists to understand that the nucleus itself, the center of the atom, is itself made of even smaller things called protons and neutrons. These are heavy particles that you can knock out of a nucleus if you fire, say, a particle emitted by a radioactive atom. If you bounce it into a nucleus, sometimes you can chip off these things. You see them coming out. They're detected in experiments from about 1919 until 1932. And this leads to a pretty good then understanding of where the chemical elements come from, because you have these three particles now: the proton, this positively charged particle, the neutron, the electrically neutral one, and then the negatively charged electron that goes around the outside. And so if we think about some basic atoms like hydrogen or helium or carbon, we can understand their properties in terms of these basic building blocks. So hydrogen, which is the simplest chemical element, is just a single proton with a single electron going around it. The next simplest element is helium, which has got two protons, two positive charges in the nucleus, two neutrons, two of these neutral particles, and then two negatively charged electrons in orbit around that. And then say the carbon in our apple pie, well, that's 6 protons and 6 neutrons and 6 electrons all joined together to form the atom. So these laboratory experiments really result in a great triumph, which is a proper understanding of the chemical elements and the patterns that you get in the periodic table. You have to add in quantum mechanics as well, but that ultimately allows you to explain what you observe in chemistry. And it also now opens up a way to understand, or to answer that question: where do the chemical elements come from? Because if we now think of atoms as being built of smaller components, then you can then imagine a way in which they might have been assembled through some process. And from sort of from the 1920s through to the 1940s and 50s, there's a big theoretical and scientific effort to try to understand where the different chemical elements come from. And the basic assumption is that hydrogen, being the simplest element, is the basic building block of all the others. And you need to find a way of joining hydrogen together to make helium, oxygen, carbon, all the other elements in the periodic table. Now, to do this requires fantastically high temperatures. Scientists know this because protons are positively charged. So if you try to bring two protons together, they will exert an enormous electrical repulsion on each other. So to get them to join together to make a heavier element, you need to get those protons going incredibly quickly. And so scientists or physicists and astronomers start to think, well, are there places in the universe where you have temperatures that are high enough to fuse hydrogen together to make helium, presumably the next simplest element? And they eventually realized through a combination of astronomical measurements and theoretical calculations that indeed there are places in the universe that are hot enough, which are the centers of stars, like our sun. So we now know that at the center of our sun, the huge pressure caused by the sun's gravity generates very high temperatures, around 15 million degrees Celsius. And at those very high temperatures, hydrogen nuclei, protons, are whizzing around very, very quickly. They bang into each other, and through a series of steps, they build helium. So they build the next heaviest element in the periodic table. And if you have much heavier stars, then eventually they heat up to a temperature where you can start to fuse helium into carbon and into other elements. And in this way, you can build up through the periodic table. And then when these stars die, they waft the chemical elements that they've made in their cores out into space and enrich the universe in heavier elements. So this is a photograph of a planetary nebula called the Bow Tie Nebula, which is what our sun will likely look like in sort of 4 or 5 billion years from now, when it's run out of its hydrogen and sort of basically wafted away its atmosphere into space and enriched the space around it in carbon and in helium. If you have a really massive star, then they die rather more spectacularly. They will eventually fuse all the elements all the way up to iron. So that's quite, well into the periodic table. And then they undergo these violent explosions called supernovae, which then blast heavy elements out into space, which are another source of the chemical elements. And we now also know, intriguingly, in the last few years, that it used to be thought that the chemical elements basically came from stars like the sun or heavy stars that went supernova. But we now also suspect that actually a large fraction of the really heavy elements, so I'm talking about elements like gold and platinum, are actually made in these extraordinary astronomical events, which are when two very dense objects called neutron stars, which are essentially the dead cores of very heavy stars made entirely of neutrons, smash into each other. And when they smash into each other, you get basically huge numbers of neutrons flying out through space, and they coalesce and form heavy elements like gold, platinum, and so on. And one of these neutron star collisions was observed for the first time, I think back in 2017, by an astronomical observatory called LIGO, which is actually a gravitational wave observatory. And they detected these neutron star collisions. Telescopes pointed it to this place in the sky that they'd seen the signal from. And they estimated, based on the light that was emitted, that about 30 solid gold Earths had been produced in one of these collisions. And it's now suspected that a large fraction of the gold in any ordinary piece of jewelry came from the collision between neutron stars. So which is a pretty extraordinary thing to think. So this next image, this is a periodic table that was put together by an astronomer at Ohio State University called Jennifer Johnson, and her research looks at the origins of the chemical elements. And this is sort of a representation of our best knowledge of where all the different chemical elements come from. And you can see actually there's a wide variety of different sorts of astronomical sources that make the different elements. You've got exploding massive stars, exploding white dwarfs, merging neutron stars, dying low mass stars, all kinds of things. So we have a pretty complete understanding of the origin of the chemical elements now, thanks to both these laboratory-based experiments on Earth and studies by astronomers. And this picture was relatively well understood, even going back as far as the 1950s and 60s, although people didn't know about the neutron star stuff back then. But there was one obvious problem, which was to do with the composition of the universe as a whole. So for example, if you look at a star like our sun and measure its chemical composition, essentially by looking at the light that it emits and searching for signs of different chemical elements, you'll get a picture that looks a bit like this, where the sun is about 73% hydrogen, 25% helium, and then a tiny fraction of the other heavy elements. You can see those tiny slices in the foreground, oxygen, carbon, then everything else is only around about sort of 2%, and everything else is hydrogen, helium. But the weird thing is that, well, we know helium is made inside stars. So why is there so much helium compared to the other elements? Because, helium gets made, but then helium gets turned into carbon and oxygen and other things. So there's way more helium than you can explain from just the process of stars turning hydrogen into heavier elements. And it was realized that this amount of helium could only be explained if there was another source of the chemical elements. In other words, another kind of cosmic cooker somewhere out there that was making helium. And it was realized that eventually that actually the place where most of the helium in the universe was made was actually right back at the beginning of the universe during the Big Bang. So in the very, very first few minutes after the Big Bang, the whole universe was this superheated plasma full of protons and electrons and neutrons. And at these very high temperatures, huge amounts of protons and neutrons were forced together, making helium. So actually, most of the helium in the universe was not made in stars, but made in the Big Bang itself. And in fact, this the ability of the Big Bang theory to predict the amount of helium in the universe, which it does very accurately, is one of the big pieces of evidence in favor of the idea that the universe began with the Big Bang. Of course, now we have a lot more evidence from a load of other sources as well. So we now basically, through a combination of stars and the Big Bang, we've got a pretty good understanding of where the chemical elements come from. But then the next obvious question is, well, okay, if the basic building blocks of the chemical elements are protons and neutrons, well, where did these things come from? How did they form? Are they like Newton's, indestructible particles that God created in the beginning, or did they form in some process, perhaps even earlier in the history of the universe? Well, again, we get a sort of first clue to answer this question from particle physics experiments that are done in the 1960s, where essentially you use giant particle colliders that fire electrons at protons, and they discover in these experiments that the proton and then the neutron are actually not fundamental particles. If you look inside them, they're actually made of even smaller particles called quarks, and which are held together, bound together inside protons and neutrons by these particles called gluons, so-called because they basically glue these quarks together. So quarks and gluons are actually, strangely, forever locked up inside protons and neutrons. So we've never actually seen a quark on its own in any particle physics experiment. They always seem to be stuck inside these particles, but we have lots and lots of evidence for their existence, basically by firing electrons into protons and seeing how they bounce off. And by looking at the way they bounce off, you can infer that there are three objects inside the proton. But we can sort of now start to think, well, okay, in the same way that the elements are made of protons and neutrons are made of quarks. So was there a process where they formed in the early universe? And the answer is yes. And if you actually go back to before around a millionth of a second after the Big Bang, the temperature in the universe at that time was so high that it was actually hot enough to melt protons and neutrons. So protons and neutrons actually sort of melt into this very strange state of matter, a sort of super hot liquid known as a quark-gluon plasma, which is basically a sort of a soup of quarks and gluons whizzing around at temperatures of trillions of degrees Celsius. So as you go back in time towards the Big Bang, the temperature of the universe gets higher and higher, and eventually you get to a point where you have these quarks and gluons flying about freely. And then as the universe expands and cools, these quarks and gluons stick together and form the protons and neutrons that we find inside every atom. So we now again have a sort of an understanding of where the protons and neutrons that make up all the chemical elements come from. And in fact, there are experiments that are done here on Earth where we can probe these sorts of temperatures. So amazingly, there's this amazing machine just outside New York called the Relativistic Heavy Ion Collider, which is a large particle accelerator which fires gold nuclei. So the nucleus of gold around this ring smashes gold nuclei into each other. And when they collide, they generate these enormous temperatures of trillions of degrees and melt the protons and neutrons inside them to produce this strange state of matter, this quark-gluon plasma that filled the universe in the very earliest moments. And this is an image of one of these collisions where you can see basically all this sort of fuzz you can see is thousands of particles flying out from the collision. And by looking at the way that these particles come out from the collision, the scientists are able to infer that they've made a little blob of this quark-gluon plasma stuff right in the middle of their experiment. So that was a very sort of rattle-stop tour of our current understanding of where the stuff that makes up our universe comes from. And before we can make any more progress, we now need to have a little review, I think, of what the basic ingredients are. So we said at the beginning that we have electrons that go around the outside of the atom, and then we have the up and the down quark. These are the two quarks that make up protons and neutrons in the nucleus of every atom. So actually everything in the universe, well, at least all the ordinary matter, every star, every speck of dust, every planet in the universe is made from just these three particles bound together to form a wide variety of different atoms and different chemical elements. But these are not the only particles that we know of. There are actually a bunch of other particles that don't form matter in the way that the up and down quarks and the electrons do, but it nonetheless play an important role in our understanding of the ingredients of the universe. So there's another particle called a neutrino, which is a sort of a very strange, ghostly particle. It's electrically neutral and it has almost no mass. Now, neutrinos are produced in lots of different processes. In particular, they're produced in the nuclear reactions at the center of the sun that make helium. So actually, there are, I think, trillions and trillions of neutrinos passing through you every second, but you don't notice them. They go right through you, right through the Earth and out the other side. And that's basically because they don't have any electric charge. They don't interact with ordinary matter very strongly at all. It's very, very rare that a neutrino actually bumps into an ordinary atom. So you have these four, what we call matter particles, and for reasons we don't understand, it was discovered in experiments during the sort of latter half of the 20th century that there are additional heavy copies of these particles. So all the particles in that first column have heavy, unstable versions. So, for example, the electron has a heavy, unstable cousin, if you like, called the muon, which is that little square on the bottom right, which has exactly the same properties as the electron, the same charge, interacts with the forces in the same way, but it's 200 times heavier. and it only lives for about 2 millionths of a second before it decays into electrons. We don't really, and the same goes for the quarks. There are heavier versions of the quarks called the charm and the strange quark. We don't really understand why they exist. And there's actually a third column even to this table with even heavier, even more unstable particles. For example, there's something called a tau, which is the really heavy version of the electron. And one of the big mysteries in particle physics is why we have these 12 matter particles. Why are there 6 quarks and then these 6 blue things, which are known as leptons? We don't know the answer to that. There are also, in our current understanding of particle physics, the forces of nature. So the force that holds the electron in orbit around the atom is the electromagnetic force. That's also the force that's responsible for electricity, magnetism, light, and that has a particle associated with it called the photon. There are also the gluons that we already discussed. They're the things that stick the quarks together inside protons and neutrons. And then 2 other strange particles associated with something called the weak nuclear force, the weak force, which is another sort of strange force that doesn't really stick things together, but basically allows different particles to transform from one into the other. And the final piece of this picture, which is known as the standard model of particle physics, is the Higgs boson, which is a famous particle that was discovered at CERN about 10 years ago. And I'll tell you a little bit more about that in a moment. So we have this theory, the standard model, and it describes all the particles that we've ever seen. It describes the forces that they interact through, and it does this really spectacularly well. In terms of understanding the stuff in the world around us and also the history of the universe, it's very, very powerful. But there are some questions that it's unable to answer, particularly as we push further and further back towards the moment of the Big Bang. So if we go back really, really far back to the first millionth of a second after the Big Bang. As I said, at this time, the universe is extremely hot and dense, full of matter and very, very large amounts of energy. And in this very early period, there's so much energy in the universe that there's this constant process of creation and annihilation that's going on. So to understand this, I should introduce another idea, which is that all the matter particles that we know about, so by which I mean the quarks, the electron, and the various other ones that I described to you, have what we know as anti-partners or antiparticles. So these are sort of mirror images, effectively, of the ordinary particles, which have exactly the same properties, but they have the opposite charges. So, for example, there's an antiparticle of the electron, which is either called the anti-electron or the positron, the same thing, which is exactly the same as an electron, except it has positive charge. You also have an anti-up quark, an anti-down quark, and so on. And in this first millionth of a second after the Big Bang, you have this constant process where particles and antiparticles are being created from energy. And then when a particle and antiparticle meet up again, they then annihilate, they turn back into light or into some other particles. And this process is going on continuously. Now, then when you get to this moment, 1 millionth of a second after the Big Bang, the universe has expanded to such a degree that it's cooled down, and it's cooled down to a point where there isn't enough energy to make more particles and antiparticles. So what happens is all the particles and antiparticles that exist at that moment very quickly meet up with each other and annihilate. And this event that I think Frank Close called the Great Annihilation, which is basically this cataclysm where almost all the particles and antiparticles in the universe annihilate each other, and you get left with mostly light. And according to the standard model, what this should have left us with is a universe that contains no matter and no antimatter at all, because according to our theories, these two sorts of matter are basically identical copies of each other. There's a perfect symmetry between them. And so you expect equal quantities of each to have been made, and therefore for them to have completely annihilated each other. So the universe will basically look like this infinite black void with a few particles of light coasting through the darkness. And that's what the universe ought to look like, according to the standard model. But of course, we know that the universe is full of stuff. It's full of gas and dust and galaxies and stars and planets. And this is one of the biggest problems outstanding in particle physics, which is trying to understand how was it that enough matter survived the Big Bang in order to create all the stuff we see around us. So this is a pretty big problem. I'm sure you agree. Any theory that predicts the non-existence of its own authors is probably in trouble. But it's not actually the only problem that we can't answer at the moment in terms of the origins of matter. If we go even further back in the universe's history, so this time we're pushing back into that first sort of fraction of a second to 1/1,000,000th of a second after the Big Bang. Around 1/1,000,000th of a second after the Big Bang, another critical event happened that should have led to us living in a completely uninhabitable universe, or rather not living in a completely uninhabitable universe. And this event is to do with this particle that I mentioned, the Higgs boson. So the Higgs boson is famously extremely difficult to explain and understand, but I will do my best. So it's, in essence, the reason everyone got very excited about the Higgs boson when it was discovered in 2012 is that it actually was telling us about the existence of something more important, which is something called the Higgs field. So the Higgs field is a sort of invisible field that fills the whole universe. If you like, you can think of it a bit like a sort of a fluid of some kind. And the Higgs field plays a very, very important role in particle physics. It's this field that ultimately is responsible for giving mass to all the fundamental particles in the Standard Model, at least the ones that have mass. So the basic idea is that if you imagine this sort of Higgsy fluid that's everywhere, when a particle like an electron moves through this Higgs field, it effectively gets sort of slowed down by the Higgs field and imbued with the property of mass through its interaction with the Higgs field. Now, the Higgs field itself is invisible. You can't see it, you can't taste it, you can't touch it. But one of the ways you can tell it's there is if you can make a disturbance in it. It's a bit like the air in a room, right? You can't see the air, but one of the ways you know the air is there is you can hear sounds moving through it. That also, and you're not suffocating. Well, the idea with the Higgs is the same. So if you can hit the Higgs field hard enough, you can make it ripple, and that ripple shows up as a new particle, which is the Higgs boson. If you prefer a slightly more cartoony picture, this is sort of another little representation of what's going on. You have your field, which is a quantum field technically, and the Higgs boson, this particle, is a little disturbance, a ripple in this quantum field. And actually, this is true not just for the Higgs boson, but for all the particles in the Standard Model. So electrons are little ripples in something called the electron field. Photons are ripples in the photon field, and so on. And this is really how we think about the basic ingredients of the universe in particle physics. Now, the reason that that's the Higgs field. So the Higgs field is the thing that gives mass to all the particles that we know about. And the Higgs field is unique amongst all the fields that we know about in nature in that it has a fixed value everywhere in space. So that means if you go to a bit of empty space and you look at the sort of fields in the vacuum, you would find that all the other fields, so like the electromagnetic field, the electron field, the quark fields, these all have a value that is very close to zero. But the Higgs field is different. It has a finite value. It's a bit like having a sort of water level that's been raised to a uniform height throughout the whole universe, if you want to think of it as a sort of a liquid of some kind. And it's the value, this non-zero value of the Higgs field that's responsible for determining the masses of all the particles that we know about. So basically, the larger the value of the Higgs field, the more massive every other particle should be. The smaller the value of the Higgs field, the less massive particles should be. Now, 1/1,000,000th of a second after the Big Bang, as far as we understand, this was the moment when the Higgs field effectively switched on. So the Higgs field went from having a zero value everywhere in space to the modern value that it currently has. And when it reached that value, the particles that we know about acquired mass, and the electron, the quarks, took on the properties that we know them to have today. So this process is very important because if the Higgs field had landed at a different value, then we would end up with particles that behave very differently, and you might end up in universes where it's not possible to form atoms, for example, and therefore there's no wobbly flesh-colored things made of atoms like us. In fact, the thing that's really troubling about this is if you try to figure out what are the likely values for the Higgs field, you find two really troubling results, which is that in the very early universe, the Higgs field should either have turned on basically as far as it could go, so switched on all the way to an incredibly large amount of energy, which is, in particle physics units, 10 billion giga electron volts, which is a very, very large number. It doesn't really matter for the sake of the argument what this means, but basically, if the Higgs field had a strength this high, then every particle in the standard model would become so massive that it would collapse into a black hole. And the universe would look a bit like this. Basically, it would just be, well, it would be black and it would be full of black holes, but certainly no atoms and no stars. The other possibility is that the Higgs field could have ended up with a zero value. And again, this is very bad, because if it has a zero value, that means electrons and quarks and other particles don't have any mass, and that means atoms can't form. And you end up with a universe that's basically a kind of hazy mess of massless particles zipping around close to the speed of light. But again, there are no stars, no planets, no people in this universe. And the weird thing is that we now know from experiments that the Higgs field has a value that is neither 10 billion billion nor zero, but a number around 246 giga electron volts. Now, this is very, very hard to understand. Basically, in order to get this Goldilocks value, you have to do an incredible amount of fiddling around with the fundamental constants of nature in a way that's completely implausible. So it basically looks like somehow the universe has arrived at this particularly fine-tuned value that allows everything that we see around us to exist. But if we were to sort of look at this from a sort of naive perspective, we would expect the universe to either be entirely made of black holes or to have no atoms in it. And understanding this is a really big mystery. So we have these two big mysteries really about the origins of matter. How did matter survive the Big Bang? And then also, why didn't the Higgs field basically kill us? Why didn't it make the existence of atoms impossible? And these were two of the really big questions that people are trying to answer in fundamental physics at the moment, and particularly at the Large Hadron Collider, the experiment that I work on. So back 10 years ago or so, there were lots of candidate theories that might have explained some of these problems. They had fancy names like supersymmetry, extra dimensions of space. Some of them predicted the existence of tiny black holes, which led to the Daily Mail predicting the end of the world as a result of the LHC, if you remember that. But basically, the idea was that if you wanted to solve these mysteries, you would expect to find new particles of some kind or some kind of new phenomena at the Large Hadron Collider that would help us understand, potentially answer one or maybe both of these questions. So let me tell you a little bit briefly about the LHC. So this is a photograph of the area outside Geneva showing the route of the Large Hadron Collider. It's a 27-kilometer particle accelerator, and what it does is it fires protons around and around in a ring, accelerates them to a tiny fraction below the speed of light, and then it smashes them into each other. And physicists like me then study those collisions in search of signs of new particles, new forces, or something else going on in the collisions that we can't explain with our current theory. If you're curious, this is what the LHC looks like. It's basically a very, very long blue tube in a very, very long tunnel. And at certain points around this ring, that tunnel opens up into these large subterranean caverns where you have these giant particle detectors. So this is one of the particle detectors known as CMS. It's this gigantic, essentially 3D digital camera, 15 meters high, 25 meters long. You can see a little guy in a hard hat standing down the bottom there for scale. These are enormous instruments, but their basic job is to record what happens when the protons smash into each other and to scour these collisions for the signs of new particles. So about 10 years ago now, on the 4th of July 2012, the LHC snared its first big prize, which was the discovery of this Higgs boson particle that we were just talking about. And here's a picture of a load of physicists getting very excited and cheering and so on that day. So that was a really great day. And it was felt that was the sort of first step on a journey that would allow us to start to answer some of these big questions. But if you followed the physics news over the last 10 years, you will have read an increasingly large number of slightly pessimistic headlines. So here's a few examples. One result back in 2011 that was testing this theory called supersymmetry, which is one of these theories that could have answered some of these questions, and basically finding no evidence of it. Again, another article from a few years later, popular physics theory running out of hiding places. LHC keeps bruising difficult to kill supersymmetry. So you sort of get the idea. Basically, it'd been a story of a fairly gloomy story in a sense. If you were hoping to see signs of new physics that might explain some of these mysteries, well, the LHC was basically offering us very little clue about where to go. The Atlas and CMS, these two experiments, have found the Higgs, but otherwise there'd been no evidence of all the different sorts of new particles that might have been hoped to have been found at the LHC. That is until about 2 weeks ago or 2 or 3 weeks ago, where you may have seen this news story on the BBC or in other outlets. Machine finds tantalizing hints of new physics. So I will try now to, I don't know if you saw this story, but it caused quite a stir. This was just at the end of March, and it was a result reported by the experiment I work on called the LHCb experiment, which is one of the 4 big detectors at the Large Hadron Collider. This is a kind of a story that's been brewing for several years. Basically, LHCb and my colleagues at LHCb have seen an increasing number of strange results that we don't seem to fit with our current theory of particle physics and could be hinting at something new. So I will try to explain what exactly we're seeing. So the first thing to say is LHCb, the B in LHCb stands for the B quark, which is one of the 6 quarks. It's a sort of very heavy version of the down quark that you find inside protons and neutrons. This is usually called the bottom quark, but at LHCb we call it the beauty quark because we'd rather be beauty physicists than bottom physicists, basically. And the collisions at the Large Hadron Collider produce billions and billions of these beauty quarks every year. And they're very interesting things to study because they live for a short amount of time once you create them, and then they decay into other particles. And by studying the way they decay, we can get information on what forces, for example, exist in nature that allow beauty quarks to decay into a variety of other particles. This is an image of one of the collisions recorded by LHCb, and you can see all the different particles zooming out from the collision point, which is down on the bottom left. Now, this particular result that was announced a couple of weeks ago was in looking at 2 related processes. So the first, basically 2 different ways that this beauty quark can decay. The first is where a beauty quark decays into a strange quark, which is the next heaviest version of the down type quark, and then an electron and an anti-electron, this E plus E minus. And then my colleagues compared how often basically beauty quarks decay in this way to how often they decay to a very similar related process where instead of having electrons and anti-electrons in the final states, you have muons and anti-muons. So there's a lot of jargon flying around, and I apologize for that. But muons are basically, I'll just remind you, the heavy version of the electron. They're basically identical to electrons in every way, except they have a larger mass. And as a result, if you measure how often beauty quarks decay into electrons and how often they decay into muons, you would expect that these 2 processes should happen equally often. And that's because all the forces in the standard model treat electrons and muons identically, more or less, apart from the small effects of their different masses. So we have this very accurate prediction from the standard model, which is that if you divide the number of B decays into muons by the number of B decays into electrons, that number should be 1. In other words, those 2 things should happen equally as often, and it should be 1 with a very high level of precision. You can see there's a very small uncertainty. This is a theoretical prediction basically based on what we currently know about the standard model. But what was actually measured was this. So LHCb actually measured a value of 0.85 plus or minus 0.04. So you can see this number is quite a long way away from 1, and it has an uncertainty of about 4%, as you can see, and it's more than 3 uncertainties away from 1. So this is what we call a 3, in the sort of technical jargon, a 3.1 sigma deviation, which basically means it's 3 uncertainties away from the prediction. Now, this got people very excited because at 3.1 sigma, that basically means that the probability of this result being a random statistical fluke is around 1 in 1,000. So there's only a 1 in 1,000 chance this result is a random statistical fluke. To give you a sort of idea, if you were to say, if instead of trying to discover a new particle or something, you were trying to test whether a coin was a fair coin or not, this would be the equivalent of tossing 10 heads in a row. There's about 1 in 1,000 chance of tossing 10 heads in a row. And if you picked up a coin, tossed it 10 times and got 10 heads, you might well start to suspect that the coin was indeed biased, that it was biased towards heads. But the thing you have to be careful about is, of course, that we don't just do one measurement at the Large Hadron Collider. We actually do hundreds and hundreds of measurements. So we haven't just tossed one coin 10 times. We've actually tossed one coin 10 times, several hundred times. And if I then tell you that, well, you might start to think, well, okay, you might expect a few of these results, if you do lots and lots of tosses, to end up with 10 heads in a row. So there's still a certain probability that this could be a statistical fluctuation because we do so many measurements. But putting aside that caveat, what could be causing this? Well, this decay process in the standard model happens through the forces that we know about, which are basically the electromagnetic force and the weak force. And as I said, these forces treat electrons and muons identically, so you'd expect the two decays to happen equally as often. But if there was, say, another force of nature, some unknown force, which we'll just call force X, that which, say, for example, interacted with muons and electrons differently, well, this could provide a different way for the decay to happen and effectively change how often it decays into muons versus electrons. So what we could be seeing here is the footprint of a new force of nature that we've never seen before, if this result is borne out, although it's really at the moment too early to say for sure. Now, you sort of wait 10 years in particle physics for some new physics, and then like buses, two results come along at once. So I'm conscious that I'm running out of time, but I will try and squeeze this one in quickly. So actually just a week ago, there was another result from a completely different experiment. This is an experiment at Fermilab in the United States called the muon G-2 experiment. This is Fermilab just outside Chicago. And essentially, the experiment basically involves a big ring, nowhere near as big as the LHC. You can see a couple of people there, but nonetheless, still quite a chunky thing. And basically, what they do in this experiment is they fire muons around the ring, and they try to measure very, very precisely a fundamental property of the muon. So the muon is a fundamental particle, like the electron, as I said, and it has a negative charge, but it also behaves a bit like a little bar magnet. So it has a magnetic field around it that it produces itself. And going back, and basically you can calculate using the standard model how strong this magnetic field ought to be. And the reason this is an interesting thing to study is because, as I said, every particle that we know about in the universe is actually, we think, a ripple in an associated field. So you have, muons are ripples in the muon field, electrons are ripples in the electron field, and so on. So if you think about a little bit of space, that bit of space, even when there are no particles in it, always contains a bunch of different fields that are just sitting there in the vacuum. So when you put a muon, say, into the vacuum, it actually interacts with those fields. If you can imagine them like a sort of a surface, if you like, or like a fluid, it sort of distorts the shape of those fields around it. And so the properties of the muon don't just depend on the muon, they also depend on all the other fields that are hanging around in the vacuum. And so if you want to calculate, for example, how strong the magnetic field of the muon ought to be, you need to take into account not just the muon, but all the fields that we know about. And if you do this in the standard model, you can come up with a very precise prediction for technically what's called the anomalous magnetic dipole moment of the muon, but don't really worry about that. It's basically a number that relates to how strong the magnetism of the muon is. And you get this very accurate prediction, and this is a very difficult calculation to do. You have to use supercomputers and big teams of theorists working together, and you get this beautiful calculation, which you can see here, this number with a very, very small error on the right-hand side. And going back about 20 years, an experiment was done at Brookhaven in New York, where they measured this quantity, and it seemed to be disagreeing with the theoretical prediction. So the experiment was actually shipped to Fermilab and repeated. And when they released their new result last week, they got this value. So they measured a value that at first looks very similar to the prediction, but actually, if you study it in a bit of detail, if I highlight the last few digits, you'll see that actually these two numbers don't agree in the last four significant figures. And actually, the measurement is about 4.2 sigma away from the prediction. So about 4.2 standard deviations, 4.2 errors, which means there's roughly a 1 in a 40,000 chance of getting a random result, a sort of statistical fluctuation that would take you this far away from your prediction. Or to put it possibly in slightly easier to understand terms, this is a bit like tossing a coin and getting 15 heads in a row. So it's starting to look like there's something seriously interesting going on. And the explanation could be that apart from the quantum fields that we know about in the vacuum, it could be that there's an additional field, another force perhaps, and this force is subtly influencing the magnetic properties of the muon and shifting it away from what we expect. And so it could be and you have to take this with a reasonable pinch of salt, it could be evidence of some brand new ingredient of the universe that we've not seen before. Now, to muddy the waters slightly, this is a nice graphic that was put out by a guy called Joker, who writes a blog called Resonances on Twitter. So this is a little graph of this magnetic number that I just told you about. And on the right-hand side, you've got the experimental result in blue. And then on the left-hand side, you've got the standard model prediction, so what we think this ought to be. But then on the same morning that the result was announced, another group of theorists released a different calculation for the standard model prediction, and their value came out much closer to the experiment. I won't go into the technical details, but we can always discuss it in a Q&A if you want afterwards. So basically, the problem with this measurement is that it's not completely settled which prediction is right. So we have two predictions, both using the standard model, both just using the particles that we already know about. One of them is a long way away from the experiment. Another one is much closer to the experiment. And it could be that this is, evidence of a new force, or it could be that we just don't really understand ordinary, and we'll have to wait and see which way it goes. So just to go back to Carl Sagan, of course, what these results potentially could be claiming is something really extraordinary, which is potentially a new force of nature or some new set of fundamental particles that we've never seen before. And of course, to make a claim that extraordinary requires really extraordinary evidence. Now, but allowing ourselves to speculate a little bit, what could this be telling us? Well, one of the as I said, I described these two big mysteries to you. Where does matter come from, and why did the Higgs field not basically make the existence of the universe impossible? But there's another question which is sort of just staring us in the face when we look at this diagram of the standard model, which is we don't understand why we have these 12 matter particles, the 6 quarks and 6 leptons. They're just kind of observed in nature, and we put them into the theory by hand, as it were. And there's a good reason to think that if we are indeed seeing the first signs of a new force or some new set of particles, that it could be related to this puzzle, and it could actually be the first piece of a larger picture that will expand the standard model and allow us to understand why the basic particles that we see in the universe around us exist. It would be a bit like extending the periodic table back in the 19th century and starting to get a better understanding of what deeper structure underlies the basic ingredients of the universe. So this could be a really profound discovery. And I think what I should say is that it's really too early to say. First of all, it's too early to say whether this is really a real effect. Will it be borne out when we do more experiments? We'll have to wait and see. Will we discover there's actually something we don't understand about the standard model itself that could explain these results? But if it is real, then it could be one of the most significant discoveries in fundamental physics for the best part of half a century, I would argue. So what does the future look like? Well, LHCb is currently being upgraded. There's a big program of works ongoing right now to upgrade the experiment so that when next year the LHC starts colliding again, we'll be able to record data at a much larger rate, about 30 times faster. And that will allow us to measure these anomalies that we're seeing more and more precisely. And we will hopefully in the next few years get confirmed evidence either way of whether this is a real effect, whether it's going to kind of get more and more significant, or whether it starts to melt away into the background noise. But we will get answers, in the next few years. So it's going to be exciting. And at the same time, over in Fermilab, the muon G-2 experiment, well, they've only actually, I think, analyzed about 6% of the total amount of data they're eventually going to record. So there'll be a much more precise measurement of this quantity coming soon. Although I think for this one, it's really trying to understand the theory that will tell us whether or not we're really seeing something interesting. But I suppose to summarize, really, we've come a hell of a long way in our understanding of the basic ingredients of the universe and their origins. And it's extraordinary, really, that we can trace this story back so far, all the way back to about a trillionth of a second after the Big Bang. And it's in that first trillionth of a second where all the mysteries really lie. But we have a very good chance of getting some more information about that very earliest time from experiments that are going on right now. And these new anomalies are really making particle physics an exciting field to be in. So I'm very excited about the next few years and very keen to see what comes out of it all. So that's the end of my talk, and thank you for your attention. I will just finish with a slightly shameless plug, which is if you would like to know more about this story in more detail, with not such a kind of breakneck pace, then you can read it basically in my book, which is coming out on the 5th of August in the UK and the 10th of August in the US if you're across the pond. Thanks very much for your attention, and looking forward to having a discussion with you after the break.
Thank you very much, Harry. That was quite a tour de force. So, yeah, I think we will need a break now. There might be a few rooms across the country that might need to be removing the smoke by opening the windows. But thank you very much. That was really good. Yeah, we'll have a break now for drinks to be refilled, pits to be stopped, other tasks to be completed. Short reminder. Also, still during the break, you can put in additional questions. I see we already have quite a number of questions on our website, but if you want to add questions, the link again is sitp.online/ask. And if you don't want to put a question, but you want to have a look at the questions that are there, you can even get involved by just upvoting the ones that you would like to see answered. So, time for the break. I think we will be back at 10 past 8. British time, so see you then. Thank you. Welcome back, everyone. Thanks for all the questions received so far. I just would like to ask you to keep putting questions in, even before we're starting now. Who knows, some of you might come up with the best question of the evening still now. So let's do that. Before we start with the Q&A, a final point. After the talk, we will open our virtual online pub, the Loggins Razor, and we hope that many of you will join us. Harry, if you've got time and feel up to it, you're also happy to join us afterwards. Good. Let's look into those questions. Stu asks, going back to your talk, there's been headlines recently regarding the possibility of a fifth fundamental force. Is this truly a possibility, or is this just overhyped?
Yeah, I mean, I think you're talking about the last two results that I mentioned. So the LHCb result and the Fermilab result, they were both reported as being sort of potential evidence for a new force. So it's not, no, I wouldn't say it's overhyped. It depends. I mean, the headlines, some of the headlines were a bit over the top. There were a few headlines like the laws of physics have been broken or all this kind of stuff, which is nonsense. But if these results stand up, they could well be evidence for a new force. That's the most obvious explanation for these effects. Of course, that comes with a big caveat, which is there's still a chance that they could be a statistical fluctuation, so just random noise in the data. It looks unlikely in the case of the Fermilab result that's the case, but for the LHCb result, it's only a 1 in 1,000, so it could be. There's also always the possibility, and you have to be sort of humble about this, that there's always a possibility you missed some effect in your experiment, because the experiments are very difficult to do, require lots to take into account loads of systematic effects, and you can always miss something. It's not impossible that there's some mistake. We don't think that's the case, and both the experiments are done very carefully and very precisely, but you can never eliminate that possibility. But those caveats aside, like if it's not fluke and it's not an error, not a mistake, then it's probably, particularly the LHCb one, there is no way of explaining that number not being 1. Basically, in the standard model, that number is 1, and it doesn't matter whether you understand the theory or not. Basically, it's really clear. So if the number you measure isn't 1, there's definitely something going on there that's new, and it's probably a new force of some kind. That's like the most popular explanation. But I suppose the short answer is it's too early to say, but it's certainly the most interesting thing we've seen for quite a few years. And I think, a lot of theorists who I know, this is what they're getting really excited. They've been desperately waiting for, something new, something beyond the standard model. And this is what everyone's really pinning their hopes on, I think. So, but we'll find out. Hopefully in the next, few years, we'll get the data and we'll be able to say one way or another.
Okay. I've seen several articles who put those two experiments in relation to each other, kind of making them look like two experiments with a similar result. Is that correct, or might it be two different new forces that might be identified, or is it the same effect?
It's hard to say. There are definitely theorists that have explained both results with a single new thing. So like, I mean,
Okay.
to get into a bit more into the sort of the theory detail, there's basically the two most popular candidates to explain this effect is something called a Z prime, which is basically a new force of nature, a bit like the weak force, but like a super weak force, basically. And then something called a leptoquark, which is a weird kind of amalgam of a bit like a merging of an electron with a quark kind of thing, but another force particle, basically. So there are models involving these sorts of things, Z primes, leptoquarks, that can explain both the anomalies at once. But that doesn't necessarily mean they're connected. It could be that one of the results isn't really a real effect and the other one is, or neither of them are real, or they're caused by two completely separate new things, which is also possible. I mean, the thing that makes it suggest that they could be linked is that they both involve muons. So the Fermilab one is just looking at muons going around a ring. The LHCb one, basically there are fewer muons being produced than we'd expect. So it's the muons that are down compared to the prediction. And so it could be something that's affecting muons, and that's what's causing this effect. So it could be the same thing, but we'll have to see.
Okay. When you mentioned those numeric values for identifying the probability of this being a real effect, were you referring to what's also often called the sigma number?
Yeah, that's right. Yeah.
Okay.
So you have this, I mean, so in particle physics, there's this slightly arbitrary scale that we use to decide whether an effect is interesting. So like, if you're sort of, between 0 and 3 errors away from your prediction, that's just not interesting. No one really cares very much. When you get the reason the LHCb result made a big splash a couple of weeks ago was that it crossed what's called the 3 sigma threshold. So arbitrarily at 3 sigma, we call this evidence. So this is and the reason particle physics has this very strict sort of statistical criteria is we do loads of experiments. And there have been times in the past where some bump has shown up in some graph and people have thought they've discovered a new particle, and then they realize that actually they haven't. And it's just because there's a wobble basically in the data, and the wobble goes away when you get more data. So you need to that's why you have this high bar. So 3 sigma is where you say you have some evidence and people start to maybe get a bit more interested, but 5 sigma, so 5 errors away from the prediction, that's when we call it a discovery or an observation. And when you get to 5 errors, there's like a 1 in 3.5 million chance that you would get a random wobble that big. So it's sort of, at that point, you're basically saying, well, either it's new physics or it's some really big mistake in the experiment.
Okay, good. Okay, let's see. Next question. Next question is from Igor. He's asking, what's the new Higgs boson of theoretical physics? Something we know of in theory, but need terribly exciting, non-yet existing machinery to observe?
Well, it's interesting that there isn't, because the Higgs boson was predicted back in 1964. At least the idea behind it was put forward. So it's been something that has been assumed to exist for the best part of half a century before it was discovered, and with very strong reasons based on the standard. Basically, that all the other particles in the standard model had shown up as predicted. And Higgs was it's a bit like having a jigsaw puzzle where it's all been beautifully filled in. There's one hole. It'd be really weird if that piece didn't exist. You sort of expect it to be there in a sense. So in a way, the LHC was guaranteed either to find the Higgs or to not find it, which would be even more dramatic because it would have meant having to rethink everything. So it was a sort of win-win. You were guaranteed to win basically either way with the LHC. Going forward, like we know there are lots of big questions. I mentioned a couple of them in the talk. There's also dark matter, which I didn't even mention. So like we know that there's 5 times more invisible matter in the universe than we can see, and none of the particles we know about can explain it. So that's another really strong reason for thinking there's more particles out there. But it's not so precisely defined as the Higgs. We don't really know where dark matter is in energy, what its properties are. We have lots of ideas and experiments looking for it. But basically, there isn't a kind of single clear target. We have all these big mysteries, and we think if we look in various promising places, we might get some answers. But there's no sort of single prediction that we're trying to verify this time. It's much more exploration, going into a kind of uncharted territory and seeing what's out there.
It's more like we're now trying to break the general theory, the standard model, to make sure that we have something new to research.
Yeah, I mean, I suppose it's break it or extend it, I guess. The standard model is so successful, like it's not going to be broken as such. What we'll probably find if we do find something is that it's part of a bigger picture. It's a bit like, Newton's law of gravity it wasn't exactly broken by Einstein. Einstein just showed that it was part of a bigger picture, and it doesn't quite work in every situation. The standard model will still be there, but there'll be something bigger beyond it, which kind of improves our understanding, I guess.
Okay. Sticking to the Higgs field, we've got a question from Anonymous. Is the Higgs field the new luminiferous ether?
I guess I can see why you'd say that, because it is sort of a bit like the ether. Just for people who don't know, the ether was supposed to be some kind of invisible substance that was the medium that light traveled through. So in the 19th century, people realized that light was a wave. And so the question was, well, wave in what? Like, water waves are in water, air, sound waves are in air. So there must be, the ether was basically the stuff that wobbles when light moves through it. And loads of experiments were done, and the ether was never found. And it doesn't exist, actually. So I suppose what replaced the ether was the electromagnetic field, which is a quantum field. So the ether was replaced by something that isn't a sort of substance in the way that we would think of, water or air as being. The quantum field is something more abstract, but it's nonetheless a physical thing. And the way you can see it's a physical thing is if you get another magnet and push opposite ends of them together, you feel this force pushing back. And you can sort of even feel the shape of it, by moving the magnets around. Well, what you're feeling there is a quantum field. There's no matter there. It's just the electromagnetic field doing stuff. So these things exist, and the Higgs field is just another one of these quantum fields. And we have, from just that experiment, you can see that these things are there in the vacuum. And then at the LHC, you knock these fields, they make waves which turn up as particles. So it's not just a kind of invention like the ether. There's very strong evidence that these things are there in a way that we never found any experimental evidence for the ether in the end. It was just a kind of hypothesis, ultimately.
Good. Okay. Paul, also known as Picticule, asks, is the question, what happened before the Big Bang, Big Bang, a valid question, or is it completely incoherent?
It's a tricky one. I mean, I talk about this a little bit in the book. So I kind of only took us in the talk, I only went back to a trillionth of a second after the Big Bang, but you can go further than that. And eventually you get to time zero. And at time zero, that's when basically the whole universe was crushed into an infinitesimally tiny point. And there all our theories break down. So one of the reasons that people are looking for what's called a quantum theory of gravity, which is a quantum mechanical theory of the gravitational field, is that it's thought that to understand the moment of the Big Bang, you need a quantum gravity theory, because it's small but also gravitational, so it's quantum gravitational. But there's good reasons for thinking that that moment the universe began is unknowable in principle, and the reason basically is that very shortly after the first moment of the universe, there was this thing called inflation. It's this process, we think, where the universe expanded exponentially in a tiny fraction of a second. I think it's like 10 to the minus 32 seconds. It went from being, basically a point to something, or the size, actually strangely the size of a grapefruit, which doesn't sound very big, but it's a huge expansion. And well, basically that rapid expansion basically meant that all the information about what happened at time zero gets pushed way out of our horizon. So it's pushed outside the edge of the observable universe and we can't see it.
Yeah.
So we probably, and you never know, but we probably can't actually know what happened at time zero. So what happened at time -1 or something is presumably even more out of reach. I mean,
completely beyond us.
Yeah, that doesn't stop theorists from speculating. Obviously, I think Roger Penrose, who's a very famous theoretical, Stephen Hawking's partner, theoretical sort of colleague, has had various ideas about things you might see in the cosmic microwave background, sort of shapes in the radiation from the Big Bang that might be relics of an earlier universe. So there are people that try and look for these things, but I think they're pretty fringe ideas on the whole, and we've still got a long way to go experimentally and astronomically before we can get to that point. We're still only about a trillionth of a second, and we've got every inch you go, well, not inch, every tiny fraction of a second you go close to the Big Bang, it gets harder and harder, basically.
Okay. Yeah. Good. Let's see. What's the next question? Vicky asks, what is the best theory to explain why matter in the very early universe was not evenly distributed, but instead formed clumps? And she thanks you.
That's a great question. I mean, actually, that's related to this thing that inflation just mentioned. So there's this big mystery, which is that, so let's rewind a bit, but one of the other big bits of evidence for the Big Bang is this thing called the cosmic microwave background, which is the light that was emitted about 380,000 years after the Big Bang. So before 380,000 years, the whole universe was like the sun. It was a super hot plasma. 380,000 years cools down, hydrogen gas forms, and light travels through the universe for the first time, and that light can still be detected. So you can basically map this light in great detail, and it's basically a photo of the universe 380,000 years after it was born, which is it's 13.8 billion years old, so that's really close to the beginning. But the weird thing is that you look across this huge map of the sky, it's all about the same temperature, so it's like very, very uniform. And that's really weird because these different patches of the sky are so far apart from each other. They should never have been in contact. So how did they all come to the same temperature? Well, the answer is this idea called inflation, which is basically that you have this rapid expansion that basically blew up a tiny part of the universe to a huge size. So all these bits that were in contact close together got spread out across the whole sky. And that's why the universe looks the same in every direction. But the other thing that did was, because at the moment of the Big Bang, the universe is very small, and you have what are called quantum fluctuations, which are these rapid wobbles, quantum mechanical wobbles that are happening down at this micro scale. And inflation blows these quantum wobbles up to the scale of the universe. So you basically end up with quantum mechanical effects written across the whole sky. And it's thought that these wobbles basically are the seeds of structure that go on to form. They're basically regions of the universe where, so if they have a quantum wobble in one direction, that would have meant later on you end up with an area of the universe with more matter in it. And that collapses to form galaxies and stars. So basically the structure, the clumpiness we see in the universe is thought to be derived from quantum mechanical effects in the very earliest moments of the universe. So that's where we think the clumpiness comes from, which is kind of amazing, really.
Yeah. Okay. Andy Wilson asks, thank you for the talk. Where do the constantly moving tiny parts of an atom get their energy from? Can they run out?
Now that's a very good question. It's actually a question that bothered a lot of people about 100 years ago. So Ernest Rutherford, who's
if you know his publishing schedule for his podcast, then that doesn't surprise you. Sorry, please go ahead.
Yeah. So 100 years ago, in 1911, so when Ernest Rutherford, so he was the physicist and with his team at Manchester who discovered the nucleus of the atom, and that led to the high school model of the atom that we learned, which is a nucleus with electrons going around it. And one of the big problems with that model was, classically, if an electron's going in a circle, it should radiate energy. So if you send an electron around a particle accelerator, it gives off radiation, it gives off X-rays, and it loses energy as a result. So the same thing should happen in an orbit around a nucleus. So you'd expect the electrons basically to fall into the nucleus by giving off energy. And the solution to that is quantum mechanics, which basically says there are fixed orbits that electrons can sit on. Now, this is a sort of old-fashioned way of looking at it, but this is how it was first suggested by Niels Bohr. Basically, you could think of it a bit like railway tracks around the atom. So the electrons can only go on the tracks, and they can't fall into the nucleus because they're only allowed to move in these fixed energy levels, we call them. That's not quite the way it would be described nowadays, but that's a good enough analogy for what's going on. So basically, quantum mechanics prevents the electron from losing energy and falling into the nucleus, and that's why atoms are stable, ultimately.
Okay. Good, thank you. Next question, let's see. We've got somebody called, I guess it's pronounced Linda Later. Her question is, if the difference between particles and their antis is to do with charge, how can you tell a neutrino from an antineutrino?
That's a very good question. And actually, well, the way we can tell is if you fire a beam of neutrinos into some matter, for example, and this is what a lot of experiments do. There's experiments at CERN and at Fermilab that do this. If they have enough energy, when they hit an atom, say you have an electron neutrino, it will convert into an electron. So an electron neutrino turns into an electron. Mm-hmm. And the same will happen with a muon neutrino, turn into a muon, if the neutrinos have enough energy to do that. And you can tell whether it was a neutrino or an antineutrino based on whether an electron or an anti-electron comes out in a collision with an atom, basically. So if an electron comes out, that means it was a neutrino. If an anti-electron comes out, it was an antineutrino. So that's how you can tell. Okay. But there's another question, which is are antineutrinos and neutrinos the same thing? And this is a sort of more difficult thing to understand, but basically particles have this property called spin. They behave like they're rotating. It's a kind of, they're not really rotating, but that's a useful analogy. And neutrinos are always left-handed, and antineutrinos, which basically means they spin in a left-handed sense. So which one's my left hand? So if you imagine neutrinos going that way, then left-handed is sort of spinning like that.
Okay.
And right neutrino would spin in this direction, basically in the opposite direction, depending on its direction of motion. And neutrinos are always left-handed, and antineutrinos are always right-handed. And what we don't know is the only difference between a neutrino and antineutrino its spin? Is it whether it's left or right-handed? So if you flip a left-handed neutrino to right-handed, is that just an antineutrino? And that's not really known. That's a sort of big question that various people would like to answer.
Okay. Sticking with particles, Maurice asks, how do we know that quarks and gluons are particles rather than something else like charge density patterns if they've never been separated or been alone?
That's a good question. So there's lots of different evidence for them. So the first one is the way they were discovered was at this big accelerator in San Francisco called SLAC, Stanford Linear Accelerator, which is, I think, like a 3 kilometer, maybe even bigger than that, straight line. Basically, what they did is they fired electrons very close to the speed of light into a target, and you have your sort of target. The electrons hit it, and they come off at different angles. And the angles the electrons come off at depends on the charge distribution inside the proton. So if the proton was just a kind of like blob of charge, uniform, you wouldn't expect the electrons to get deflected very much. But what you find is that they get deflected through large angles by interacting with small points inside the proton. So you have these small, a bit like the same way that Rutherford discovered the nucleus, actually. He fired particles at atoms, and he saw that a lot more of them got scattered through big angles than he'd expect. And that basically eventually was explained because most of the charge of the atom is concentrated in a small point in the middle. Same thing, basically, but this time inside protons. And from the angles these electrons come out, you can determine the charges and how many of these things there are inside the protons. It's a bit like X-raying the proton. You're literally sort of taking an image, effectively, of what's going on inside, and you can see that these things are there. That's the first bit of evidence, but there's loads of other evidence. Like basically, the theory of quarks and the strong force can be used to predict what happens in collider experiments when you fire protons at each other, and whether you get the angles the particles come out at, what kind of particles come out. They all agree with the quark model, really accurate. So even though we've never isolated a single quark, the evidence for their existence is really pretty overwhelming. I don't think many physicists would say that quarks are not real, that they're just in the sort of figment of our imaginations. But there is one exception, which is the top quark, which is the heaviest quark. Okay. And that quark is so short-lived, it doesn't have time to form a bond with another quark. So that's sort of an opportunity to see a quark basically on its own. But they live such a fantastically short period of time, you don't actually get to see them in your experiment. You only see the things they decay into ultimately. Okay.
You mentioned protons being accelerated. I guess we're talking about some kind of elements with their electrons removed to be accelerated. What are we up to? What kind of protons are we using at the LHC or other accelerators at the moment?
Yeah, I mean, that basically the LHC, this massive machine, starts with this really humble bottle of gas. So the whole thing starts with a bottle of hydrogen gas, which looks like an ordinary industrial gas canister. The hydrogen is extracted and it's put into this box where a powerful electric field rips the electrons away from the protons. So you basically tear the atoms apart, send the protons off down a series of accelerators. So that's where they come from. They come from this little bottle of gas. And then they're sent through a series of different accelerators and eventually into the LHC. So they're guided around the ring by these very powerful magnets, and then every time they go around the ring, they get a smack from a 2 million volt electric field that accelerates them. So they orbit over and over again until they're accelerated to the speeds you want that, basically.
Okay, are there some experiments that are using things like, I think I read somewhere that lead atoms are used as kind of targets to be fired at, but that doesn't apply for the LHC, I guess.
The LHC does that. So usually there's an experiment at the LHC called ALICE, which looks at a bit like RIC, which I mentioned in the talk. So this is the accelerator. There's an accelerator in America that collides gold nuclei with each other.
Okay.
To make this quark-gluon plasma. They may also do lead. They do a bunch of other elements as well. And at the LHC, we do lead ions. So this is the nuclei of lead atoms for about a month of the year, usually get sent around the ring, smashed into each other. And that's mostly so that Alice can study this quark-gluon plasma stuff that exists in the early universe. So yeah, you can use all kinds of projectiles,
Good. Okay, back to the questions. Grady Earthling asks, is it theoretically possible that there is a fourth generation of particles after electron, muon, and tau? If not, why not?
Is possible, yeah, and experiments have looked for them. So Atlas and CMS, which are two of the big experiments of the LHC, they've looked for fourth generation particles. They haven't seen any yet, but it doesn't mean they don't exist. There's the reason. There's evidence. One of the reasons people think they may not exist is because this is a bit. I won't go into the technical details while this is true, but there's this particle called the Z boson, which is one of the weak force particles, and there were very precise measurements made of the Z boson at a previous experiment called the Large Hadron Collider at CERN, another big ring basically that collided electrons and positrons. And the properties of the Z boson depend on the number of neutrinos. And you can measure basically the number of neutrinos from the properties of the Z boson, and it comes out as 3. So there are 3 neutrinos which have masses smaller than half the Z boson's mass. The Z boson has a very big mass. It's got a massive, sorry, that was a bit of a word sandwich. It has a mass of about 90 protons. So it weighs about 90 times the proton's mass. Neutrinos have almost no mass. So this very heavy particle can decay into all 3 neutrinos. So if there was a fourth neutrino, it would have to be really heavy for the Z boson not to be able to decay into it. So way, way heavier than all the others. So we know there could be a fourth generation, but the neutrino that goes in that generation would have to be really enormously heavy, which would be a bit weird, given that all the others are so light. But that doesn't mean it's certainly possible. But so far, there's no evidence that they exist.
If it exists, it's a really rare event to recreate, I guess.
Yeah, really heavy and difficult to detect. So far, at least.
Okay, good. Another question from Igor. What's your thoughts on how this beautiful apple pie of ours will end? Which end of the universe theory is your favorite?
Oh, God. I know that Casey Mack wrote this nice book recently called The End of Everything, which looks at all these different apocalyptic scenarios. So I don't know what my favorite is. I quite like this thing called the Big Rip because it sounds quite dramatic, which is where basically dark energy, which is this force that's causing the universe to accelerate, expansion to accelerate, gets stronger and stronger as the universe gets older, and eventually becomes so strong that it tears galaxies apart, stars apart, planets apart, and eventually atoms get torn apart. So everything basically gets ripped to pieces in an instant, which would be quite dramatic, I guess. But I think as far as I understand, I'm not a cosmologist, but that's not necessarily a favored option. And it seems more likely the universe will die in a kind of gradual fading out to kind of cold nothingness. And the expansion would go on and we'll end up in a situation, which is a bit gloomy, but it's a long way off. So I guess we have plenty of time to enjoy ourselves before then.
Okay. The next question is about something completely different. Has the lockdown affected the work at the LHCD, it says here, but I guess she means LHCb where you're working at? Yeah,
that's right. It has affected things. Like, it's been obviously very difficult to get out to CERN. I mean, I've not been to CERN for over a year now. I'd be out, every few months usually. But it's been a particular problem for the people. So as I said, LHCb there's a major upgrade going on, which basically means most of the tech is being replaced. So there's a lot of work going on underground to install new parts to the experiment, and that's really has been affected. There's been obviously travel to CERN for people who have to take the hardware out there, people who are experts to do the work. It's very, very difficult. So there have been delays. I hope, hopefully, it will not impact the schedule too much. I think the original plan was that the LHC would start colliding again this year. That's now been pushed into next year, and there is a bit of a. It's going to be there's going to be a lot of hard work that's needed to make sure that the experiments are ready, but hopefully they will be. But yeah, it has affected things. I've been very lucky in that mostly what I do is data analysis, so I can be sat in my bedroom at home locked down, and I can still carry on doing most of my work. So I'm very fortunate. But my colleagues who do the sort of real hands-on hardware stuff, the real experimental physicists, I guess, that their work has been much more difficult. But hopefully things will get easier in the next few months. But we'll have to see.
Are the other experiments also being upgraded at the moment, or is there?
No, not so much. So that there is work going on the other experiments. So Atlas is one of the other big experiments. They're adding some extra what are called small wheels, which are basically bits on the end of the detector. They're not small at all. They're giant, but they're small compared to their experiment, which is enormous. So they're adding a few. I think the other experiments aren't doing too much at the moment. I think they're little bits of work, but nothing major. LHCb is the one that's really upgrading in a big way. So we're under more pressure because of that, because there's lots of activity. And then I think in about 5 years' time, the other big experiments will start to upgrade themselves in a serious way. So we're kind of on a different schedule, basically, for various reasons.
Do those works influence each other? Can you do experiments on the LHC while one of the large experiments is being upgraded, or does it bring everything to a stop?
No, it brings everything to a stop. So you can't be down in the cavern with the experiment and there's beam in the machine. So that's one of the issues is like LHCb, because we're doing a lot of work, we've got to make sure that we're ready for when the LHC switches on, because if we're not ready, it delays everyone else. And the same will be true in 5 years' time when Atlas and CMS are upgrading. If they're not ready, then it will delay everyone else as well. So everyone has to be ready. Otherwise, you can't run the collider, basically.
I see. Okay, we've got a question from Konstantin. Can you tell us more about the future circular collider, 100 kilometers, I guess, in circumference? What are the goals of this collider, and has the construction already begun?
This is a possible option for the post LHC era. So the LHC will run for another 15 years or so to about 2035. Okay. And then the people are starting to think about, well, what's the next machine? And probably the most popular option in Europe, at least, is something called this Future Circular Collider, which is a 100-kilometer tunnel in Geneva. And it will be a two-stage machine. First of all, you put an electron-positron collider in, so electrons and anti-electrons colliding. And the goal of that machine would be to basically study the Higgs boson in loads of detail. So it'd be a Higgs factory, make lots and lots of Higgs bosons. And the reason is basically to do with this problem with the Higgs field that I described, this strange fact that the Higgs field should either have a zero value or an enormous value. And one possible explanation for why it's not either of those is that the Higgs boson might not be fundamental, that it might be made of smaller components inside it, a bit like protons are made of quarks. So this machine would be able to start to probe the Higgs in a lot more detail, very precisely. And then in the longer term, eventually you would take that electron-positron collider out, put a proton collider in, which will get to enormous energies, about 7 times more energy than the LHC. And that would, again, allow you to study the Higgs, but also to look for dark matter. And the reason these anomalies are interesting is if these anomalies are real and there's a new particle, that means there's a new particle to be found. And most of the calculations suggest that they could be found at the LHC. So there's a chance the LHC could find the new particles that are causing these anomalies. But if it doesn't, then the Future Circular Collider would be able to find them. So that could be a strong argument for building it. But basically, like the LHC, this machine would have a very long program of decades, and it would look for a whole range of different things. So it'd be a very rich scientific project. But the big focuses would be the Higgs boson, and then looking to see if we can find something beyond the Higgs boson, basically.
Okay. Sticking with the experiments, we've got a question from Malcolm. Okay. We hear things like fire neutrinos at something. How do you select and collect neutrinos and fire them?
That's a good question. So basically what you do is you usually make some other kind of particle first. So you can't accelerate or control neutrinos because they don't interact with matter. They have no electric charge. So the way that we control electrons and protons is because they have an electric charge, so you can manipulate them with magnetic fields or electric fields. You can't do that with neutrinos. They don't care. They just go straight, basically. So usually what you do is you have a machine, an accelerator that will fire, say, protons into a target, some kind of target. That collision will create other particles, usually particles called pions, I think, which are basically a particle made of a quark and an antiquark. And those pions will then decay into neutrinos. So you basically focus your pions in a certain direction, and then they decay, and then you get neutrinos coming out the other end. So, or you might make muons, which will then decay into neutrinos. So that's broadly how you do it. So you start off with a charged particle, send it in the direction you want it to, and then the neutrinos decay from that, and then you've got your beam of neutrinos.
Okay. 2 questions. Can you then still control the direction in which the neutrinos will be traveling?
You can by controlling the direction the things that produce them will go. So
they don't spread out after their activities, but the neutrinos still continue.
Yeah. Okay. So there are experiments. There's experiment at CERN and also at Fermilab where they fire beams of neutrinos through the Earth to a sort of usually a detector several miles or maybe dozens or hundreds of miles away.
Like that thing in Italy a few years back.
Yeah, and then you can detect them. Yeah, so you can focus the beam. And one of my quick schemes is the idea of we have a neutrino therapy center, sort of alternative therapy, where you can go and stand a neutrino beam and have all your ills cured.
Do we have detectors for neutrinos if they're so small and don't interact with a lot? Or do we rather identify them by a gap that we see?
No, the detector's usually very big. So that the way there's a really spectacular experiment in Japan called Super Kamiokande, which is this enormous underground water tank, essentially, but it's huge and it's basically a massive cylinder. I forget the dimensions, but it's like hundreds of meters high, I think, and it's basically a big cylinder surrounded by little gold orbs. So you may have seen pictures of this thing. It's really beautiful. Yeah. And the way it works is it's filled up with water. And then neutrinos are fired from an accelerator on the other side of Japan into the water tank. And, you get, I don't know how many, I'm going to get the numbers wrong, but it's lots of neutrinos, millions, I guess, billions, trillions of neutrinos will go through the water tank. But only a few of them will bump into, very occasionally, a neutrino will bump into a water molecule. It will bump into an electron in the water. And that will create a little flash of light. Basically, the electron will start to accelerate. From being hit by the neutrino, you get a flash of light, and then the detectors detect the light from the neutrinos. So, that's how you do it. Basically, you look for the very rare occurrences where a neutrino bumps into some ordinary matter, and then you see the ordinary matter react, and that's what you detect eventually.
Good. Next question from Camille. What's your stance on string theory? Is Michio Kaku right that we are on the verge of finding the God equation? Sounds dubious.
Well, as an experimental physicist, I don't really have a stance on string theory. And the reason is that it hasn't made any experimentally testable predictions yet. So people who don't know, string theory is a putative quantum theory of gravity that, potentially you could use to understand, say, the Big Bang, for example, eventually. But despite, decades of work on string theory, so far it's not been able to make a prediction that we could test in an experiment. So as I think most experimental physicists, I very much hope that people who work on string theory get somewhere with it eventually. But at the moment, it's not yet in a place where we can use it to make sort of to design experiments or to come up with tests. So I'm a bit agnostic, I guess, on string theory, until we can get some actual data on it.
Good. Oh, I've got the usual question. We have to ask a form of this every week. Do you have a Schrödinger's cat and does it go Mion? But I think you've got bad news for our audience.
Yeah, I do not have a cat. Although I suppose quantum mechanically I might have a cat and just not be aware.
Truly.
There's a small probability I have a cat that I didn't know existed in my room somewhere. But yeah, as far as I know, I don't have a cat. No, sorry.
Good. We've got another question from Marina. How likely is it that the standard model will be thrown out?
Basically, it won't be thrown out. I sort of said this earlier, but so the standard model is so successful. It's amazing. I mean, the fact you can predict the existence of the Higgs boson 50 years ago and then build a massive collider and find it. I mean, that doesn't happen by accident. So the theory is correct in the regime in which it's been applied. So we have to remember that all our theories are basically approximate descriptions of the world. Theories. Sometimes I think theorists are quite guilty of promoting theories as if they're somehow real. The world is a theory, but that's not what the world's like. The world is the world, and we have our human beings come up with theories that we use to model what's going on in the world, and those theories can work in certain regimes, and then in other regimes they don't work. So the standard model basically works every energy regime we've explored up to the LHC's energy, which is very high energy. We suspect that at much higher energy it will eventually break down. So there'll be a regime where it needs to be replaced by something else. But that doesn't mean that the theory is wrong. It just means it's not quite a full description. And in fact, any theory we come up with is likely to not be a full description. It's always going to be an approximate description of the world, unless you really believe in the sort of the idealized dream of a final theory of physics, which is like, this inevitable perfect thing that explains everything. Yeah. I'm a bit skeptical as to whether such a thing exists, and it will always be a kind of an approximate description of what's going on in the world, I think.
Yeah, correct me if I'm wrong, but in my perception, the biggest things that we discovered in the last 10, 15 years were always experimental confirmation for things that were predicted. There was the Higgs boson, there was the gravitational waves. Is there anything out there that we are predicting and are currently building machine to try and prove it exists?
Well, I mean, that's what
we can think of.
Yeah. I think you're right in the sense that has been the story to a large degree of, kind of confirmations of established theories. But that's partly because physics is such a mature subject now. We've been doing mathematical physics for hundreds of years. It's the oldest, established science, I guess, along with astronomy. And so, we know we've discovered a lot. And as a result, the theory is very powerful and can make these predictions. But I think there may be a change coming, which is we're moving into a era possibly where experiment's going to start leading the way, because we've had this long period, before the LHC, there were lots of new theories generated, supersymmetry, extra dimensions, all kinds of ideas that answer some of the questions that I talked about in the talk. And none of them have turned out to be correct. So we're now in this position where I think theorists are much more, at least the theorists that I know, are paying much closer attention to the data rather than trying to come up with some grand idea that explains everything. It's more about what do experiments tell us? What might be a minimal thing that we can add to our theory to understand what's going on? That's sort of the way that people are approaching these anomalies. So it may be that, we're at the beginning of a new phase where we're kind of going to get new clues from nature, because it hasn't always been the case that physics has been led by theory. If you go back to the early 20th century, most of the discoveries in terms of atomic physics and nuclear physics were experimentally discovered and then theoretically explained later. And it was only later, when the theory became more established, it could start to make predictions that were then verified. So there's always this kind of back and forth. Yeah. And gravitational waves are a good example. Like, we've got the discovery of them was sort of expected from Einstein's theory, but there's now a whole new way of looking at the universe, and there are already surprising things that are being found as a result. So these are not challenging the fundamental theory, I suppose, but they're challenging astrophysics and our understanding of, like, how black holes form, or, what kind of black holes there are out there in the universe. So I think that there's going to be an age where we start to get, hopefully, exciting data from the universe that will help us refine our theories. We'll have to see, I guess.
Good. Yeah. Okay, we've got one final question, then we'll call it an evening. We saw that on the Twitch chat, a lot of people are wondering, what kind of T-shirt are you wearing there? There's a lot of interest in your T-shirt.
Oh, it's got a little spaceman on it.
So can you stand up a little bit so we can see it fully? Sorry to do that to you. Okay.
Guy on the moon. That's all.
Easy.
That was an easy one.
Thank you very much. I think that will have made a lot of people happy to finally see what's on this T-shirt. Okay, that's it. Thank you very much for that. That was really interesting. I've got a few closing notes to say. We have announced speakers for the next few weeks already, and hopefully lots of people will join in again for our next speaker. Next week, for example, we are expecting Professor Sir David Spiegelhalter talking to us about communicating statistics to the media, highs and lows during the pandemic so far. So that's going to be really interesting. If you know Professor Spiegelhalter from radio shows like... now I can't remember the name. I apologize. But he's really engaging talker and speaker, and I'm really looking forward to seeing him next week. Other than that, a reminder for our little virtual pub, the Lockins Razor. And other than that, thank you again to Harry for this wonderful talk and the very interesting Q&A. And other than that, all I can say, stay safe, stay healthy, and stay skeptical. Thank you very much. Good evening.